Alrighty, I have heaps of questions. I have a few like speculative, more like grand philosophical questions that I'd love to ask from you. But
Mm.
before that, and I'm sorry, Michael, you already did this in a couple of episodes, I know, but please, if you could humor me with, it's a very, very fascinating story where you cover the Eddington experiment, Arthur
Hmm.
Eddington, where they finally prove Einstein's theory of relativity. It's just an interesting piece of history of science in the 20th century. You probably repeated this story multiple times. So again, apologies. But yeah, do you mind kind of explaining the Eddington experiment and then how that sits along, uh, I guess how that story becomes a part of this ongoing debate on the philosophy of science?
Yeah, totally. So I'm happy to do that. And it's a great illustration of some of the issues I was talking about
Exactly,
earlier
exactly.
about the
Yeah.
how complicated it is to interpret the evidence. Um, so um, so Einstein formulated his theory of relativity, his new theory of gravitation, in its final form in the middle of World War One, and there was he there he was, a German scientist on one side of this war, which eventually came to an end. And there on the other side was an English physicist, actually a pacifist, Arthur Eddington, who was a real Einstein fan. I mean, of course, this had nothing to do with the conflict. Eddington just thought that Eddington was a really good mathematical physicist, and he saw the beauty and elegance of Einstein's theory and was able to appreciate the mathematical uh, complex well the yeah, I guess complexity of the theory. He was able to understand the theory in spite of its mathematical complexity, is what I should say. Um, and Einstein himself had realized that one thing his theory did was made a prediction about the degree to which gravity would bend light rays.
Light rays, yeah.
And that prediction was different from any kind of prediction you could get out of Newton's theory. I mean, not that Newton himself was making such predictions, but with the kind of modern estimates of the mass of light particles and so on, you could get something along those lines. So, um, so Eddington realized that you could test this prediction by taking photographs of the stars very close to the sun during a total eclipse of the sun. Now, the only reason you needed an eclipse is so that the sun is blotted out. Otherwise, you wouldn't be able to see the stars. But because the stars are close to the sun, their light's going to be bent, relatively speaking, quite a lot. Although actually, it's not that big. That's not very much bending as it kind of passes close to the sun. So the idea is to do this experiment, or really, it's an observation, not an experiment. We take telescopes to where a total eclipse is going to be and take photographs of the stars right next to the sun and compare them to the same stars without the sun, and you'll see an apparent difference in their positions, from which you can just immediately, in a very straightforward way, calculate the amount of bending, and then you can just compare that to what Einstein's theory predicts and what Newton's theory predicts, and if you get the number that Einstein's theory predicts, then it looks like Einstein is right, and you've come up with a whole new kind of evidence for this novel theory of gravitation. Anyway, so Eddington created, with the help of a bunch of people, of course, an expedition that actually went to two places in the course of on the trajectory of the eclipse. And one of those locations, the weather was much better. Actually, the location where Eddington wasn't. And they had two telescopes there. And they got conflicting results from these telescopes. One telescope gave results that actually matched Newton's prediction pretty well, and the other one matched Einstein's prediction much better. So what do you do in a situation like that? Well, it turned out that the Newtonian results, so the telescope that gave you the results that looked bad for Einstein, the photographs were a little bit blurry, so something had gone wrong with the apparatus, but not so much that you couldn't calculate a bending angle. But what had gone wrong? Nobody really knew. Eddington and his team said, well, it could be that everything's just a little bit out of focus, but we can still get the numbers, in which case Einstein would be in trouble. Or it could be that something had created a kind of systematic distortion of the image, which actually would have shifted the stars in a way that might have exactly as it were, cancelled out the extra pull because that's there because of the theory of relativity. So it might be that there's exactly the thing you want to measure, that is how far the stars look like they're kind of pushed out, has just been systematically messed up by this distortion, in which case the results of that telescope would be pretty much useless. But you don't know which it is. This is what one of these questions about what do you blame? Is it Einstein's theory you should blame for getting this false prediction?
Or the equipment, yeah.
Or is it the equipment? You know, something went wrong with the equipment, but you don't know exactly what went wrong. And there's certain things that very plausibly could have gone wrong that still would have left Einstein's theory looking wrong. Of course, meanwhile, there's this other telescope that's much more helpful to Einstein, but it's all a bit of a mess, it seems. Anyway, in the end, Eddington and his team, without really giving any reason for thinking that there had been a systematic distortion, just dismissed those results and said, the really clean results we have, well, let's just concentrate on the really clean ones. And they all support Einstein, which, as it happens, was, you know, what Eddington wanted to happen. But some of the other physicists, including physicists who performed the same kind of experiments, so people who are specialists, in other words, in these kinds of measurements, were skeptical about this. And they thought, well, I mean, it's true that those results could be systematically wrong, but we're far from knowing that they're systematically wrong. We shouldn't necessarily treat them as though they have no significance whatsoever. So this is a case where, in reality, you have two groups of scientists who I think, you know, they're both, of course, they're human beings, but they're also trying to do the best they can, just end up disagreeing on how to interpret the results because they can't agree on which bit of this complicated setup to blame. And maybe I should add that this mirror, which had caused the blurriness, hadn't caused any problems before the eclipse. And then when they went back and tested it again after the eclipse, it was working perfectly. So there was just no way, you know, it's not like they didn't go back and try and figure out what had gone wrong, but they just didn't have the information.
Yeah, it was happenstance, and fortunately Einstein was right, in fact, but he could have.
Yeah, so now we can look back, and actually, one of those critics of or people who thought Eddington shouldn't have been so quick to dismiss the results that didn't look so great for Einstein, himself led an expedition to the next really good eclipse in Australia a few years later that really did a lot to cement Einstein's theory. So he got cleaner data than Eddington had.
Okay, I didn't know about
that's a good example of how you have a disagreement, but as long as people are not being totally unreasonable, those disagreements tend to get resolved. And I'm sure it helped that his name was W.W. Campbell, was actually doing the experiment with, you know, he was right there in the place. It was his experiment. But also, you know, you do the experiment more and more and you slowly eliminate various sources of uncertainty. You don't get any blurriness the next time around. Phew, maybe something else goes wrong. But then you do the experiment again at great inconvenience, because these obviously it's not easy to find an eclipse and you have to travel to out of the way places.
Oh, certainly. Yeah.
Science kind of gets there in the end, but not in this very methodical way where it's able to, as it were, make up its mind at every step of the way exactly how to treat the evidence. Instead, you have a whole range of opinion with different views about what might have got wrong that tends to converge over time, just because the more evidence you get, the more you kind of satisfy different scientists' suspicions or reasons for skepticism.
But this is excellent, because I think this perfectly leads us to this idea of how does science self-correct. It's not even something we do consciously, but it's kind of a part of that public institution, as you outlined. Because it's interesting, when Popper and Kuhn, when they were doing their work, especially Popper, it was, as you said, kind of like this, to try and find an answer as to where human beings completely got it wrong with World War II and all of that mess. And now I think this debate on the philosophy of science is perhaps most pertinent for our times, post-COVID, because as we all know, science became deeply a contentious political matter, where, you know, it's interesting how, and this is why I love studying the philosophy of science, because just in the general public, a lot of the criticisms that certain people like Anthony Fauci and all these other quote unquote figureheads of science, although we know no such thing exists, but just for, let's say, the public facing figures of science, whenever they self-corrected, whenever they said, oh no, masks work, masks do not work, yada yada, this was seen as a bad thing. But I would assume if we were following your iron rule of explanation, it's quite the contrary. This is exactly what science should be doing. But anyway, could you kind of expand on how does science self-correct, and why? I don't want to say we should blindly trust science, but we should probably understand that paradoxically, science works by its failure to work, if that makes sense.
Yeah, I think there's a sense in which it's just not true that science self-corrects. And there's a sense, but so I don't mean that science doesn't find the truth eventually. I mean, it very, very often does, and perhaps most of the time it does. We're now that we've had a few hundred years of it, we can see this long string of successes. So it kind of tends to get there in the end, at least on the kinds of questions we've asked of it so far. But I think it doesn't get there by going back and fixing its mistakes. So take the Eddington thing. It's not as if we still don't really know what happened with that telescope. And we didn't make progress by figuring out what was wrong with it. We didn't make progress by reaching some agreement on what was wrong with it. So you'll actually find people arguing even today about whether Eddington should have disregarded that data or not. But not relativity physicists. They could care less, because since then what's happened is, instead of those old experiments being kind of, as it were, corrected or cleaned up, they just kind of got submerged between more and more data that was better in various ways. Fewer things went wrong, or there's just sort of the equipment became more reliable as people used it over and over again. They developed new techniques that eliminated certain sources of error. This tends to happen, and so what you have is not so much a kind of a complete understanding looking back of why all the experiments came out the way they did, but more, you have so much recent data that's quite compelling that you just stop worrying about all the old complications and confusions and mysterious results. So that it's really more a kind of a swamping process by which science makes progress. And something like the pandemic, where people are really, their lives depend, or at least it seems like they might depend on making sense of the science, really kind of brings you face to face with that element of science where can be quite a lot of disagreement on how to interpret the data, especially early on when it's not very good. It's as it was, say, with something like masking. And you have different scientists disagreeing with one another about the effectiveness of masking, using different techniques, putting their faith in different techniques. So some people were much more reliant on controlled experiments that had been done with masks that seemed to show they weren't as effective as you might expect. Other people were much more convinced by experiments that were sort of like mechanical experiments, which showed that a mask just would trap the great majority of the virus and so on. And it's not the case that all of this stuff, first of all, the public sees these arguments, these disputes, which just seem to be based on different subjective estimates of which source of information is more reliable. But then they also don't get to see some subsequent process where everyone explains why things came out the way they did earlier on. Instead, they see opinions shifting, but they don't really see the sort of the self-correction that some people claim exists, that might be responsible for that convergence of opinion. In fact, I would say 99% of us now still couldn't really give a clear story about how the thinking about masking evolved over the course of the pandemic, and that's pretty typical of science. It's not so much self-correction as just sort of doing more and more empirical testing, and that's where the iron rule comes in, because that's, in some sense, and so the iron rule really encourages you not to argue a lot, once you've kind of looked at the empirical data that exists on the page, as it were, you can't spend too much further time arguing about the significance of that data. The thing to do is to go and do more experiments. So the own rule really encourages scientists to just pile layer upon layer of new data,
Sure.
swamping the old data, and that's kind of how scientific opinion is formed much of the time, I think.
Yeah.
So it doesn't really look like people expect science to look, which is a little bit like those 20th century, those noble 20th century figures, the way they expected it to look. It's not. You see science being made, and you don't see everyone kind of agreeing on what to think about the evidence. Okay, well, we're not sure yet, we just need a bit of this, bit of that, then okay, well, that means this, methodical, stepwise, and then backing up if there's an error, going back and saying, oh, we figured out what went wrong, okay, now it's all good from now on. Instead, you just see a kind of chaotic process that's mainly a sort of a headlong data production process, where just more and more evidence gets thrown onto this big unruly pile, until finally enough scientists declare themselves satisfied enough that some sort of consensus emerges. And that doesn't look methodical enough to be science. And yet that is pretty much exactly how science works.
Yeah, and case in point would probably be climate change, right? Because if you think about it, there's no such thing really as climate science. Like climate science itself are myriad amounts of sub-disciplines where scientists working in their own fields, they probably don't even talk to each other, but they're working on their tiny bit of research, hopefully following the iron rule of explanation, and then kind of, I don't want to call it a synthesis because that sounds like they're all in agreement, but there's something emerges that, okay, this is the current hypothesis within these conditions that we put in. And most scientists would say, okay, look, climate change, it's a problem. We got to do something about it.
Yeah. And with climate change, you have a big solution to this problem, which is the UN body, the IPCC, which does try to synthesize everything. As you say, there's all these different people. There's people who work on the oceans, there's people who work on clouds, there's people who work on just putting things together into a big mathematical model, but they don't understand exactly why these are the right principles for clouds and these are the right principles for oceans. And it's in principle, it's a collaboration, but as you're exactly right to say that 99% of the time, scientists are just working on their own little bit of the story. So you need somebody to put it all together, but you also run into this problem of what I call the essential subjectivity of science, that you have a lot of disagreement. You have a lot of different rival principles or models, and it's with these different models of, say, clouds, for example, ways of dealing with clouds and models. You have the same kinds of disagreements you have with different measuring instruments. One group thinks their model is better, and the other group thinks their model is better. And eventually, hopefully, we'll figure it all out. But meanwhile, we need to make decisions. We need to know what to do about climate change. How much to spend and what way to spend on avoiding at least the worst outcomes. And so we don't have time to wait for the scientists to all say, okay, now we have enough data, we can definitely tell you what's going on with the clouds. Instead, you have the IPC is basically not just synthesizing the data, but synthesizing opinion and saying, okay, well, there's a spread of opinion about these models. We can't change the fact that there's not one agreed way to deal with this stuff. But what we can do is sort of average over that range of opinion. So if they do their job well, and some climate change skeptics worry that that's all a stitch up and they're not doing their job well. I don't think that's right. But if they do their job well, then they're kind of at least finding the center of opinion and taking a kind of a snapshot, or taking the temperature, if you like, of the range of opinion about these things at the time, and delivering it up to policymakers so that they can actually make somewhat well-informed decisions about what to do. But that's an operation that actually exists outside of science as it's normally pursued. In most sciences, there's nobody doing that. There wasn't a group of arbitrators sitting there looking at the eclipse experiments back in 1919 to decide exactly which ones we should trust and how much, and saying, you know, we're fairly sure that Einstein is right, or something like that, the sort of thing the IPCC says about certain levels of sea level rise. It would be too expensive and too complicated to have that. And in a way, you don't really need it. It's not urgent. And as long as the iron rule kind of sends all scientists sort of charging off back to the lab, back to the observatory and so on to bring in more evidence, then eventually with just a little bit of luck and a lot of determination and focus and funding, the picture will clarify. But there is a need with these things like the pandemic, with COVID, things like climate change, to have somebody that is very scientifically well informed, but exists outside of the normal scientific structure, to actually do this interpretation in a sort of real time, as it were. It's because science has this character that we've been talking about, that you can't just kind of, as it were, open up the scientific journals and see what the current state of knowledge is, because in a sense there's no such thing as the current state of knowledge, or at least there isn't, insofar as such a thing exists. It's more like an average over a wide range of opinion, expertise, and so on. So it's, you know, it means that interpreting science is hard work.